Hello students, so we are going to start a new section of the transport phenomena or the fluid dynamics series of lectures, that is computational fluid dynamics, or in short it's called the CVD. There are different tools and different softwares and cloud computing methods which are based upon CFD, and so we will take them one by one. Today we will be discussing about the discretization method. Now there are three different discretization methods. Now let us first understand what is the discretization method is actually is. In this method, suppose there is a pipe through which water is flowing. Now what we do in a discretization method is we uh, divide the domain. I mean, this is the point where the water is entering the pipe. We would divide, we'll call this as the domain, and we divide it into a set of grids or meshes. Okay, like the one which has been shown in a magnified manner, and each grid or mesh will act as a control volume. By control volume, we mean is that volume where the conservation laws apply. And the conservation laws, that is, which are mainly related to mass, energy, and momentum, are applied or valid in the control volumes. So this is actually a control volume which has been magnified. So in this way, we have different control volumes. Now, the shape or the type of mesh used for the discretization, it depends upon the geometry or the conditions. Most of it is the geometry. So you can have two-dimensional meshes which can be formed by triangle or square. It's called quadrilateral or diagonal. Or we can have three-dimensional meshes like tetragonal, hexagonal, wedge, and prism. And you can see that by hexagonal we mean that there are 6 faces. By prism, we all know what is a prism is. Prism are also sometimes called wedge dislocation. Wedges are pieces of wood which are thicker at one end and thinner at the other end. They are used to connect different wooden compartments. So this is an example of a wedge, as has been shown. So similar to that, the one mesh structure can be. It actually depends upon the structure or how in where we are actually putting the meshes. Like this is an example of a hybrid mesh for an IC engine valve. So you can see that tetragonal meshes has been used here, and whereas hexagonal meshes are applicable here. So by using these different types of mesh, we actually are getting different control volumes. Okay. Now, after we have done the meshing, there are three different ways by which this discretization method can work. One is called the finite difference method, one is the finite volume method, and the finite element method. Now, the finite difference method, that is the first one, it approximates the derivatives based upon the difference between the two grid points. So we have two different grid points. It takes the difference between them, and then it is used in approximating a derivative. FEM, on the other hand, is based upon polynomials, different types of polynomials used, piecewise polynomials. Whereas the FVM, the volume flux volume method. This is or the finite volume method. This is based upon conservation of flux, and this is what we shall be using in this lecture. We shall be discussing about FVM in this lecture. Okay. Now moving forward, the finite volume method, as previously told, is based upon flux conservation. So from this equation, this is a volume integral. So this value q, or this parameter q, it is representing the conserved variables, the mass, energy, momentum. So rate of flow, or volumetric rate, this part is being balanced by the fluxes. This is what this equation actually means. That means if there is a local or a global conservation of physical quantities, that is mass, energy, and momentum, is taking place, this is mainly because of the fact that the flux is leaving one control volume and it is going into the another control volume. So this phenomena has been represented by this equation, and it is known as the finite volume method. Okay. Now another aspect of control volume is if you we usually consider a point at the center of any control volume, and that point is represented as P. And so instead of so this is in fact an extension of the finite volume method. So what we have done here, we have represented the conservative variable. Here it was q, but here we have represented it by phi. The flux vector is the same as in the previous case. The area is being replaced by S. The only thing is that we had no source term here, but we are assuming there is a source term. So this is more of a phenomena where considering the whole system, whereas this phenomena is when there is exchange taking place from one central volume to another. So there has to be a source, and that source is represented by this volume integral. Okay. There are tools used for the computational studies. The first term of them is called an approximate integral. The approximate integral says that the volume integral can be simplified in terms of this value phi. This phi p, it represents any dependent variable, and the suffix p indicates at the center. So if there is a control volume, what is the value of that quantity which we are trying to conserve, or through on which the equation is based, at the center, and this when multiplied by the change in volume, it is equivalent to the volume integral. And the same goes for the surface integral, where a summation of the fluxes through different areas is done to find the surface integral. So these are the approximate integral for simplified approach. Now there is a balance equation across the volume as per the discretization. The balance equation is this is the surface part, and this is the approximate integrals which are being simplified, and so we get this balance part. Now this is mainly because the fluxes are facing each other. So there is two central control volumes. This is one control volume and this is another control volume. So face-to-face flux exchange takes place between these control volumes. And since that is why this phi QP is being considered, because we are considering that the central point between the two faces. So that happens to be the center point of the mesh. Now, the finite volume method, as previously told, is based upon this flux quantization, and it is the most important part of this finite volume method. Is now by flux quantization. Now, when we are considering, when we are considering the fact that there is a flux quantization, although there are different regions in a flow where the flow is not at all uniform. So the usage of flux quantization is actually dependent upon different types of schemes based upon the nature of the flow. Like we have an upwind stream. Up by upwind, we mean that we use the quantity or we take the difference between the up topmost flow and the one which is at the bottom. So if a phi f is the flow, is the flux, so this phi f will be equal to the one at the center. We can associate this phi with the one at the center, that is the p, only when the velocity is has crossed a certain value. Now the problem with this flux or the upward scheme is these become inaccurate, or these are applicable when there is high speed flow going on. That means a uniform but a high speed flow, and this fails when there is a steep involved. Okay, so this, if there is a steep involved, so there will be large difference between the velocity at the top and the velocity at the bottom. So the accuracy is questionable at that time. However, for very fast moving liquids where the Reynolds number is more than 2000, that is even in turbulent flow, we can use this scheme. The next type of scheme for flux quantization is the central difference. So the central difference is basically, it takes the average of average of fluxes of two neighboring control volumes. However, this is mainly applicable for laminar flow. That means there is the pressure difference, or the velocity of the flow is considerably less. Another aspect to this flux quantization is a quantity called the Peclet number, PE. P is just the ratio of the transport taking place due to convection by the transport that is taking place through diffusion. So a high value of P indicates that the convection component is much higher. That means the flow is faster. However, for stagnant water or slow moving water, the Peclet number usually is very less. Now, Peclet number is applicable in heat and mass transfer as well, but we shall be mainly focusing on the fluid transfer or the mass transfer. So for the fluid and mass transfer, this Peclet number is equal to the velocity of the fluid flow, the length, characteristic length, divided by the kinematic viscosity. That means the viscosity, dynamic viscosity divided by the density gives us the kinematic viscosity. This is the expression for the Piglet number. And so for central difference, we usually have a high Piglet number. That means where the flow is laminar and the speed is not that much. It's a low speed and it has got a lower diffusion. Okay. Now, there are other types of schemes for flux quantization. One of them is called the high resolution scheme. Actually, a lot of schemes come under this high resolution scheme. This is basically based upon the fact that there are regions where there are generation of shock waves or there are very steep gradients. So for those regions we need to limit the flux. So there is something called a phi limitation associated with the flux, and these phi limitations are mainly done by this high resolution scheme. So they have got an additional advantage or having a flux limiter. Like this TVD, there is a scheme called in high resolution scheme. There is a scheme called TVD. TVD stands for total variation diminution. Total variation diminution. And in TVD there are different phi limiting cases like min mod, then you have super B, then you have Van Leer. These are different phi limiting limiters, and they all are based upon a switch between a high order and a low order schemes, and the flux they are based upon F phi L and phi R, where L and R are simply the left and right fluxes. So we have different combinations and different equations or different relationships in this high resolution scheme, which is considering this low, the left and the right fluxes. Okay. Now, after the flux quantization has been initialized and everything, there are different numerical methods on which the equations are solved, and this FVM method, one of the case studies or one of the examples where this FVM method is very much applicable is in the dam spillways. Now, spillways are backdoor paths for the water to be released when there is a flood or when there is an excess and the dam needs to release some water. Then the spillway comes into the scenario. Now, this spillway also needs to be analyzed, and for that we can use the FVM method. And in the FVM method, we use a two-phase Navier-Stokes equation and followed by a method called volume flow method. Now, what is this volume flow method is? The volume flow method is based upon tracking the air and the liquid interface. So VOF, volume flow method, it tracks down the fraction of water F. F represents the fraction of water in each control volume. Okay, so let us go here, like here, the volume of flow method. So if we are representing F as a fraction of water, so if the value of F is equal to 1, then it indicates that the control volume is full of water. However, if F is equal to 0, it means it is full of air, and F is usually is between 0 and 1. Now, the equation to get the value of F is simply the rate of change of the fraction of water is equal to velocity, the dot product of velocity and the fraction gradient. Okay. And if when we have obtained the value of F, that is a fraction of water present, we can relate this with the density and viscosity for each control volume. Now the next is the two-phase Navier-Stokes equation. Now Navier-Stokes equation, as we all know, is the analog of the second law of Newton's in the case of fluids, and it is based upon the fact that there are certain forces acting on the fluid and which are being compensated by some gradients of velocity and windy velocity. Okay, so this is there are when we say two phase, we mean that there is a conservation of mass taking place and there is a conservation of momentum, which is actually the original Navier-Stokes equation. Now we associate also heat with it. So if there is a heat dissipation taking place, so this also gets into the, if you make the Navier-Stokes equation, we blend it with this heat flow, then you actually get the two-phase Navier-Stokes equation, and this is the equation for the heat dissipation, where during the process, if any heat gets generated, so then we can relate it with the thermal conductivity of the material. Okay, and we have the usual Navier-Stokes equation. Well, it is discussing about the change in the volumetric rate, and it is associating it with the different forces acting on it. Now, using all these parameters or all these informations or tools, we can computationally derive or computationally see what is my or how my flow looks like. Like for example, here now there are two boundary conditions. One is that the inlet flow rate is constant and the outlet flow rate. These are the two boundary conditions. Outlet flow rate, that is P atmospheric. This is outlet flow rate. Okay. Now this is the result, simulated result that we have obtained after putting all the initial values. So you can see that there are different colors associated with different regions of the fluid. Now this is a dam, and where the fluid is flowing through the dam, and there are slipways. Now the velocity profile here, you can see that the the areas where there is a very high speed are represented by red, and the lowest ones are represented by blue. So you can see velocity profile. Secondly, you can have an air-water interface between the water and the air. So there is water is said to be the white and air, and so water is said to be the white one. Air is said to be the white one, and water flow. So you can say, so the places where there is more bluish in nature, like this one. So here the water content is more. And next is the pressure. There are regions where there are high pressure, and there are regions where there are low pressure. So the pressure distribution can also be obtained by doing simulation based upon the initial conditions discussed. And also there is a combined velocity streamlined and volume of flow. So this is the combined one, and it actually shows how the flow and the interface are reacting with each other. So we can get a pictorial representation of the fluid flow and its interaction, and the water flow through the dam and its interaction with the air. And this actually governs, will be the source of governance for a spillway in a dam to work.